In this lesson, we'll talk about properties of graphs of various functions. Let's look at basic shapes of functions that are commonly used. The first such function will be absolute value function. Some of you may already know the shape of absolute value function, but if you don't quite remember it, we can use table of values and develop a few points to plot. So if the input is -2, remember absolute value leaves the answer positive, so the output will be 2. For -1, the output is 1, absolute value of 0 is 0, absolute value of 1 is 1, and 2 is 2. So you can plot those points. -2, 2 is here, -1, 1, 0, 0, 1, 1, and 2, 2. So now we can recall that the shape of absolute value function is a V shape like this. Let's graph it. Okay, so what's the domain of absolute value function? Well, recall that the domain is the set of all possible x values that we can use to plug into the expression and be able to evaluate. Since we know how to take absolute value of any real number, the domain would be the set of all real numbers. You can also see this by looking at the graph. If we project the graph onto the x-axis, entire x-axis will be shadowed by the graph. The range, well, now we need to think about the possible values, possible f of x. But we know that absolute value leaves the answer positive. The least that we can obtain is actually 0. We can confirm this by looking at the diagram. The range is everything from 0 to the infinity on the y-axis. So we can write interval from 0 to infinity. 0 is assumed because f of 0 is equal to 0, and infinity always has a round bracket. Infinity is a concept, there is no last number. Is this graph symmetrical? Do we see any symmetry here? Well, yes. I see a symmetry in y-axis. It looks like an open book. If you close it, this part of the shape matches the other part of the shape. So we have symmetry in y-axis, as with subindex y. And another feature of this graph, we see a special point. This point will be called vertex, and that's a point 0, 0. So that's a point when the line is bending and kind of reflected from x-axis back to the infinity. This vertex is a point when the line y equals x is reaching x-axis and doesn't proceed any farther as normally would, but it is reflected over the x-axis up because the values of absolute value of x are always positive. And the section to the left of y-axis is actually part of the equation y equals -x, but only the part that belongs to the negative x's. And this is something that we should expect because absolute value of x, according to the definition, it is either x or -x. It is x if x is positive or 0, and it is equal to -x if x is negative. So in a way, we see two pieces of simple linear functions that we know very well, but they are connected at the point 0, 0. And we create a new function by using one piece from one function and the other piece from the other function. You will learn later that such functions are actually called piecewise functions. The second function that we'll look at is a square root function, root of x. So if we want to create a table of values, we need to think, can I take any value for x and be able to evaluate root? Or just some values are good and the others are not? Well, we can't take a negative x because root of a negative doesn't exist in real world. DNE stands for doesn't exist. Therefore, the smallest value that I could actually plug in instead of x is 0, and then any other values that are higher. I chose the numbers that are easy to calculate, perfect square numbers. But even if this number is not a perfect square number, we evaluate by using calculator. Okay, since we figured out that the lowest number that we can take for x is 0, therefore domain of our future function must start from 0. And then we can actually take any number that we wish higher than 0. Could be as high as we want to. We're still able to calculate square root of it. So from 0 to infinity, that's domain. Okay, let's come back to the table of values. Root of 0 is 0. Root of 1/4 is 1/2 because it's root of 1 and root of 4. Root of 1 is 1, root of 4 is 2. Okay, now we're ready to graph. Let's plot those important points. 0, 0, that's a starting point. 1/4, oh, that's a very tiny number, but if it's very close to the y-axis, the value is actually a lot higher because it's 1/2. So 1/4 very close to the 0, 0 on the x-axis, but 1/2 on the y-axis, a lot higher than the x. Now the next number 1, 1 is somewhere here, and the following one is 4, 2, somewhere there. Obviously in both cases I assume that 1 square represents 1 unit. Okay, and now what we need to do is to join these points, join it smoothly. So the graph looks somehow like this. Obviously it will proceed higher and higher. Maybe not so steep, but sooner or later the function will assume as high values as we wish to. So the range must be from 0 to infinity. We can observe the range by projecting the graph onto the y-axis. It's hard to see it here, but like I said, the graph is rising all the time, so sooner or later we'll cover every single value on the y-axis starting from 0, but never below 0. And finally, here we can also talk about the vertex. Notice that this square root function is actually half of parabola. If it would be graphed that way, the other half, then we would have a sideways parabola, and half of it is a square root function. So no wonder that we also talk about the vertex. It's like vertex of parabola, but a sideways parabola. So the vertex here is the starting point, very important point, the starting number of your domain. So that's 0, 0 as well. What else we could say about this function? It is increasing. It is all the time increasing. While the previous function, it was decreasing in the first half until 0, and then it was increasing after 0. The next function is a reciprocal function, 1 over x. Think for a second about possible domain. What kind of values can we take for x and be able to evaluate 1 over x? Well, anything except for 0, because 1 over 0 doesn't exist. We can't divide by 0. So 0 has to be excluded from the domain. All other numbers are fine. So the domain for this particular function is all real numbers but not, so we subtract, a set composed of one element, 0. Notice that here we're subtracting sets. So writing something like this doesn't make sense. Some people do that, but that doesn't make sense. Why? Because the capital R represents a set, and then we subtract a number, not a set. It's a number. So it's totally different categories. It's like subtracting dollars from tables. They don't match. They have to match in order to be able to perform subtraction. So that's why I put this wavy bracket around 0 to indicate that I'm taking away a set composed of one point, one number. That could also be written in interval notation by saying, okay, we start from negative infinity and going up to 0, skip the 0, and then it's a union from 0 to infinity. So either like this or like that. If the set of real numbers misses just 1 or 2 points, I tend to write this way because it's just shorter. However, if you're required to give the answer in interval notation, that would be the desired form. Okay, since we know already what's the domain, we can fill up the table of values. The function f is giving us reciprocal of every input. So if the input is -2, the reciprocal is -1/2. Reciprocal of -1 is still -1. Reciprocal of -1/2 is -2. Reciprocal of 0, that's why we took 0 out of the domain. We can't really do it. 1 over 0 doesn't exist, so we can write doesn't exist. Reciprocal of 1/2 is 2, reciprocal of 1 is 1, reciprocal of 2 is 1/2. And let's plot those points. -2, -1/2, -1, -1, -1/2, -2. You can easily predict that if I will choose -1/4, I will end up with -4, so closer to the y-axis. And also, if I would choose -4, the reciprocal will be very close to the x-axis, -1/4. So we can predict that if we join those points and we want to find out how this graph behaves further, it will get closer and closer to the y-axis and also closer and closer to the x-axis. Now, 0 is not in domain, so we don't have any value here, which means that this graph will be broken. It's not connected with the other part on the other side. However, we can still plot the other part. So 1/2, 2, 1/4 would be 4, 1, 1, 2, 1/2, and 4, 1/4. Similar idea, except that it's in different quadrant. Let's connect those points. The graph looks somehow like this. We already figured that 0 is out of the domain, but what about the range? Well, if I project my graph onto the y-axis, all positive values are covered, but 0 is not. There's no x such that the f of x would be 0. Notice 1 over x will never be 0 because the numerator will have to be 0, and numerator is constantly 1. So it's impossible to have 0. Any other point than 0, it will be shadowed by the graph if we project it onto y-axis. That means that the range is the same as the domain. All real numbers, but not 0. Written either this way or in interval notation, the same as in the top. Now look again at this graph. Is there any symmetry that you can notice? Well, I see a central symmetry, symmetry about the origin. How can we recognize this? Well, if we take a point that belongs to the graph, for example 1, 1, and graph a line connecting this point with the center to the other side, then at the same distance on the other side you will find a point that also belongs to the graph. So if I start with a point 1/2, 2, and go to the other side of the 0, 0 point of the origin, at the same distance as my point 1/2, 2, I can find point -1/2, -2, and it also belongs to the graph. If a graph has such property, then we are saying that the graph is symmetrical about the origin. SO, symmetry in origin. This graph has another important feature. As I mentioned before, the graph is approaching certain line. For example, it's approaching vertical line from the left towards -infinity and from the right towards +infinity. Such a line is called an asymptote. So this vertical line x equals 0 is an asymptote. And we can give the equation of this asymptote. It's just x equals 0. Well, there's another asymptote. It's a horizontal line. This x-axis is also an asymptote, just because the graph is trying to approach this line. Either when x's are going towards infinity, the graph is nearly 0, or when x's are going towards -infinity, the graph is nearly 0. So we have second asymptote, the x-axis, and the equation of this asymptote is y equals 0. The following shape will be of a cubic function. So x cubed, cubic function. Here I can take any number and cube it, so the domain will be all real numbers. There's no problem with domain. Okay, let's check couple points. Notice that here I can't take two large points because when you cube it, it will go out of the graph. So negative 2 cube is negative 8, negative 1 cube is negative 1, 0 cube is 0, 1 cube is 1, and 2 cube is 8. Well, 8 already goes out of the graph, but not too much. We can still try to plot it. So negative 2 and 8, that's negative 5, 6, 7, 8, approximately here. Negative 1, 0, 0, 1, 1, and then 2, 5, 6, 7, 8, approximately here. Now we need to connect all those points. It would be good to figure out how the function behave around 0 because, well, here's very steep, but then it has to go across and then again it's very steep. So in order to know a little bit more about this function around 0, maybe check a couple more points. For example, if I choose negative 1/2 and cube it, I have negative 1/8. So negative 1/2 is somewhere here, but the value is very, very close to the x-axis, so it's tiny here. Therefore, it looks like the graph must be quite flat around the 0 and then very steep farther from 0. Similarly, if I choose 1/2 and cube it, I have 1/8. So another point is somewhere here very, very close to the x-axis. Okay, let's try to graph it. That's our cubic function. So what's the range? Well, range, if you look at the graph and try to project it onto the y-axis, the whole y-axis will be shadowed by the graph. Therefore, the range is also all real numbers. As a matter of symmetry, we have similar situation as in the graph of reciprocal function, that if we pick any point from the graph and go across the origin to the other side with the same distance, we'll find a point that also belongs to the graph. So yes, we have symmetry about the origin, the same as in reciprocal shape, symmetry by origin. What else can we say about this function? Well, it looks like a snake and it's always increasing, all the time increasing. If we go back to the reciprocal function, if we start from the left, the graph is decreasing. So it is decreasing for negative x's. And then if we jump to this second section, it's also decreasing. So the function is decreasing for all negative numbers and it's also decreasing in all positive numbers. Here the scale is the same as usual. 1 square represents 1 unit. Finally, we have very interesting function. It's kind of new. Many of you probably didn't see it yet. It's called greatest integer or sometimes step function. How is it defined? Basically, if we take any number on the number line, so here's my number line, 0, 1, 2, -1, -2, and if I pick any number here, for example, 1/2, then the greatest integer of this number gives me the closest integer from the left. That means in this case, if that was 0.5, the greatest integer of 0.5, it is marked by this double braced bracket, is equal to 0. It is the integer that does not exceed our number and it's closest to this number, as close as possible. So always to the left and the highest integer that does not exceed this number. That's what we take. So for example, if I have -0.9, the greatest integer that does not exceed this number is -1. So the value for -0.9 is -1. For the value of -0.1, even if our number is here, the greatest integer that does not exceed this number will have to be looked at to the left of it, the highest integer that is still lower than our number. So -1 as well. Greatest integer of 0 is still 0 because it's an integer and does not exceed 0. So it's fine. Greatest integer of 0.5 is still 0. 0.99, which is somewhere here, when you look to the left, and look for the closest integer. Well, that's 0 again. 1, the greatest integer is still 1. 2.3, somewhere here, the greatest integer is 2. Formally, we can say the greatest integer of certain number is defined in the following way. Let's locate the integral interval of this number. So for example, if x falls somewhere here, the interval that I think of is this, and we take the left-hand side integer of this interval. Okay, maybe we should start plotting those numbers. -0.9, greatest integer is -1, the value is here. Again, 1 square represents 1 unit. -0.1 is also -1. Notice that any point in the interval from -1 until 0 will result in a value -1. So we can join all those points, right? And what about the endpoint of this interval? Greatest integer of -1 is -1. So we're going to include this point. However, greatest integer of 0 is not -1 anymore, it is 0. So this point will be excluded because the value is actually here. Therefore, we put an open circle to indicate without the endpoint, the whole segment without the endpoint. And then we jump to the next interval. So points like 0.5, 0.99, 0.1, all of them will result in the value 0 until we reach 1. Then the result is 1. And then for the numbers that are a little bit higher than 1, let's say 1.5, the greatest integer of this number is 1. So the segment goes here all the way until we reach the 2. At 2, the greatest integer is not here, it is actually here. It has a value 2. And so on and so forth. So let's graph this. As you see, this function will jump every single time we meet an integer. It's higher. That's why it's called step function. And the left-hand point of each segment is included. However, the right-hand point is excluded. So we should draw a hollow circle on the right-hand side of each segment. Step function like this. Okay, let's look at the domain of this funny function. Again, recall that domain is the set of all x values that we can actually take and evaluate greatest integer of. But any x value, any real number, has its greatest integer, has an integer that kind of supports it. It's closest from the left, closest but not exceeding it. So the domain is all real numbers. We can also look at the graph. If we project the graph onto the x-axis, every single number will be covered, will be shadowed by the graph, just because this point is not shadowing, but the next one is, right? So at those jumps, one of those points, one of the segment, is still covering the integer value. What about the range? Each segment will cover only one point, the integer one. So this one is just 0. Every segment covers just one point on the y-axis. So that tells me that the range is composed not of the segment, but of the set of all integers. They are discrete, they are not connected. However, we have a nice letter that describes this. It's just a letter Z. The set of all integers, that's the range. And the jumps happens every time we hit an integer. So we can say at all integers. So what else can we say about this funny function? Is it increasing? Well, nearly. However, there are some sections that are constant, not really increasing. So overall, we can say that this function is non-decreasing. That means either increasing or constant.